Hello YouTube, this is Eric from Coder Snacks. Today we're going to talk about the board game Mastermind. Let's get started. This question is simple algorithmically, but we can make improvements as we write a solution. Additionally, it's easy to miss some edge cases. This is a problem where we have to be careful. And for some of us, it was a fun game from our youth. To be honest though, I always found it a bit frustrating as a kid. But now, I can get my revenge by sicking my computer on it. Before we get started, what kind of questions do we have? Do we want our solution to be extensible? In our problem statement, we said there will only be 4 colors, and the answers and guesses will only be 4 characters, and we could build our solution based on those assumptions, but we may want to extend to more colors and more characters later. How often or how many times do we expect to call this function? There are some extreme things we can do if we think we'll call this function many times. How do we calculate near hits? This is an important detail for this question, and we want to make absolutely sure we understand before coding. For purposes of this question, we'll assume that we want our answer to be extensible if possible. We'll discuss calculating near hits in a moment, and we don't want to make any assumptions for now about how often we'll call this function. First, let's talk about near hits. Here's the example from our problem statement. The general idea is, for each letter in the guess, we want to mark it a hit if possible, then a near hit, but we can only use each letter of the answer and guess once. The first orange in the answer is a hit with the orange from the guess. They're in the same position and the same color. However, the second orange in the answer doesn't match up with the first orange. We've already used it for a hit. In the same way, the blue in the guess only makes a near hit. It's the same color, but wrong position, with one of the blues in the answer, not both. So we have one hit for the first orange, and one near hit for one of the blues. The yellows in the guess don't match anything, those are misses. This suggests a naive algorithm. Check for all the hits in the answer and guess. Then, for each letter in the guess, check the answer for a near hit. To prevent making multiple matches for the same letter, we will blank out the letter in the answer when we have a near hit. This means we have to handle hits first. We shouldn't blank out a letter that's a hit in a later position. Let's write some code to do this. We'll start by making lists for the answer and guess so we can blank out matches. Then we'll check for hits. If the answer and guess is the same in the same position, add a hit and blank out the 2 squares. Next, we check for near hits. For every character in the guess, skip it if it's blanked out, otherwise check every letter in the answer, and if there's a match, add a near hit and blank the letters in the answer and guess. At the end, return our answer. We'll write a few tests, maybe more than usual. We want to make sure that this is working the way we want. But when we run it, everything seems okay. What's the runtime complexity of this code? It depends. Normally we would say O of n squared. In the worst case, for each letter of the guess, we're looking at each letter in the answer, and there are n letters. N times n is O of n squared. But be careful. Since n is constant in our problem statement, we could also claim that this is O of 1. But if we want to think of this as extensible, we should say O of n squared and look for something better. We're duplicating some work here. When we go to calculate near hits, we're looking at all the letters in answer over and over again. But we don't care where the letters are in answer for near hits. We can't use a color for near hits more often than it appears in the answer. If we count how many times colors appear in the answer, we can use that instead. To take this a little bit further, we can count colors in the guess as well. Then, for each color in the guess, we can add the lesser of the number of times it appears in the guess or the answer to our near hit count. Let's go ahead and code this up. This time we'll use a default dict to store our counts of how many times each color appears, and we'll only loop through the answer and guess pair once. If we see a hit, we'll record it, otherwise we'll add the colors to their respective dictionaries. At the end, we'll take a sum of the minimum of how many times each color appears in the guess and answer as near hits, and return our answer. We run the code, and it seems to be working. What's the runtime complexity here? It looks like O of n plus k, where k is the number of colors, since we have a loop over each character, and then a loop, the generator expression, over colors. But the loop over colors is bounded by n as well. Even if we allow thousands of colors, we won't have more than O of n colors in these dictionaries. This code is O of n. Another solution here is using lists instead of hash tables for these counts, since we know beforehand how many colors there are. This seems faster because list access is faster than hash table access. However, the list solution really is O of n plus k. The lists are length k and you have to loop through the whole list. Additionally, if you go with this approach, you have to convert the letters to numbers, which also takes code and time. Remember though, although O of n looks better than O of n plus k, it doesn't mean it is in actual code. Big O notation ignores constant factors, and the O of 1 of a dictionary lookup is definitely worse than the O of 1 of a list lookup. You would have to test to see which is better for your case. Here, the difference is probably minuscule. Best is if you can discuss these trade-offs and then do performance testing. But we can actually do better than either of these. Maybe. Sort of. If we look at our problem statement again, it says 4 letters and 4 possibilities for each letter. This means there are 256 possible answers and guesses. We could make a table of the 256 possible guesses and the 256 possible answers and pre-compute the answers for all 256 squared possibilities. While 65,536 possibilities is a lot, it easily fits in memory, and if we're using this in a game server and speed was critical, it might be worth it. This solution is O of 1 after the pre-computation. All we have to do is a single table lookup. To write the code for this, first we'll make a lookup table. If we had a class for Mastermind, it would make sense to make this a class variable, but since we don't, we'll make it global. Next, we need a method to generate the table. We'll generate a list of the 4 to the 4th possibilities using itertools, and then for each answer guess pair, we'll put the answer in the lookup table. Next, we'll make a new method to get the result out of the lookup table and change our test call to reflect this. We run it, and we can see it takes a while to generate the first answer, but after that it's fast. Now that we've mastered this problem, let's look at some challenges. How would you write an AI to play this problem? That is, a program that makes a guess, gets an answer back, and makes further guesses, trying to guess the answer in as few tries as possible. Additionally, what is the method that minimizes the maximum guesses required to get an answer? I'll link to a Knuth paper that solves the 6-color version in 5 moves. Can you do better in the 4-color version? How do you make this more extensible? Making the lookup solution more extensible may be infeasible, but you should be able to modify this code to handle more characters and more colors. Finally, as a simpler one, our generate table method takes twice as long as it needs to. How can we fix this? Next time on Coder Snacks, we are doing it live. We're going to solve a problem without editing and discuss afterwards what could be better about the resulting code and interview. We looked at Glassdoor for a recent interview problem from Facebook, and here's what we found. Try and solve it and see how your answer compares to ours. Don't worry, I made plenty of mistakes. I hope you got something out of this video. If you have any questions, comments, something I've missed, or problems you want answered or covered, let me know in the comment section below. And if you enjoyed this video and want to see more, it would be great if you liked the video, subscribed, or both. I really appreciate it. See you here next time on Coder Snacks.